Okay, so we are now ready to study the normal distribution. We defined two alternative approaches to handle continuous random variables, and we are going to use them to study the normal distribution. And as I said, the normal distribution is the most important distribution in any field of science. In natural science, in many natural phenomena follow normal distribution. I don't know if why, I don't know why, but something like for example, heights and weights of animals and plants are very much like normal distribution. And I don't understand what it means, but velocities of the molecules in the ideal gas follows normal distribution. I don't know what it is. Uh, but anyhow, so normal distribution is found in many places in nature. And also in social sciences, we usually assume that the distribution is normal, errors are normally happens. For example, we assume that the distribution of a test score is normal. So based on that assumption, we develop standardized scores. We assume normal distribution to do that. And in finance, if you assume that a financial assets, like the return from an asset, is normally distributed in the future, then you can calculate the appropriate price for that asset using Black-Scholes equation. Using the Black-Scholes equation in finance, it also assumes normal distribution for the financial returns. And in management and quality control, manufacturing quality control, the General Electric's Six Sigma principle is based on the assumption that the manufacturing errors are normally distributed. So normally distributed, and then they develop some principles called Six Sigma using the normal distribution assumption. So of course, we are using normal distribution in statistics, and which is also very important. And these are not what we are going to study in this case. Like, these are just examples, but we are going to use normal distribution for a different purpose. I am going to show you in the following chapters, most of the statistical measures are actually normally distributed. So that's how we are going to use normal distribution in statistics. So normal distribution has two parameters. Like binomial distribution had two parameters. Also, the normal distribution has two parameters, and they are the mean and the variance. And of course, the variance should be strictly positive. And these two parameters can specify all the probabilities of the normal distribution. So a normal distribution can take any number, any real number, either negative or positive, but what you need is just two numbers. If you know the mean and the variance, then you can calculate any probability. That's the how much you can compress the information into two numbers, two parameters. And we write x, or random variable x, follows normal mu comma sigma squared. I did not explain that. It is Greek letter mu. It's a mu called mu, and this is the another Greek letter sigma. So sigma squared is the variance. So x follows normal, or simply n. I may use this one in this slide, in this course. And so I don't need to talk more about the mean and the variance. And you may think rather this way. So the reason why we often use the mean and the variance to describe data, the reason why we are using them is because they are parameters for the normal distribution. So normal distribution is more important, and that's what makes the mean and the variance important. So if you know the mean and the variance, then you can imagine it's like if you assume that the distribution is normal, then you know how it would behave. So in the normal distribution, the mean and the variance contain all the information. So that makes these two measures so important. So this is the bell curve. The density, probability density looks like this, but when you change the parameter values, the density function changes this way. The probability density function is centered around, so think about blue, the mean is 0. So 0 is the center. So it's peaked at the mean, but when you change the mean to +1 or -1, the probability density has a parallel shift, moves parallel, like shifts to the to have a new center. It is always centered around the mean. So orange is centered around 1, and the green is centered around -1. So the mean gives center, and then the bell curve will be symmetric around the center. The other parameter, sigma squared, will capture how flat or how steep the curve is. So like blue is the 0, 1 bell curve. So mean 0 and variance 1. Bell curve is this much step. But when you increase the variance, it will become more flat because the random variable is more variable, more spread out, and it's more uncertain. So it can take even like more extreme values, like larger and smaller values. On the other hand, if you reduce the variance to 0.5, then it will be more concentrated around the center. So it will have more probability near the center and lower probability on the extreme values. So also intuitive, right? Like smaller variance means smaller variability, smaller spread, smaller uncertainty. So most of the probabilities will be close to the center, right? So basic properties of the bell curve. Always symmetric about the center. So because of the symmetry, the median is always the mean. You know, right? It is symmetric, so when you cut the probability at the center, it's exactly 50-50. So the cutting point is also the median. So the mean equals the median. And the probability peaks at the mean, so the mode is also the mean, right? You remember mode is the peak of the density histogram, and it ranges from -infinity to +infinity. Even though it looks like there is no probability here, but actually the probability is always positive anywhere on the line, but it approaches to 0 as it goes to the infinity. So it approaches to 0, but never hits 0. So any number is actually possible. Theoretically, mathematically, any number is possible, but extreme numbers are extremely unlikely. That's what I wanted to say here. Probability decreases, always decreases, goes down. And as I said, change in mu will make a parallel shift, and change in sigma squared will make like flattens or widens the curve. So you know, the bell curve was like a good-looking, well-known probability distribution function. And in the following chapters, all the random variables will be approximated to a normal distribution, right? So So this is so important. But all the probabilities will be calculated based on a normal distribution. But the problem here is that the bell curve so that means we need to calculate the area below the bell curve, which is not possible by hand. So you need to use a computer. So and another problem here is the bell curve will change as the parameters change. So you cannot calculate the bell curve by hand. How can you do that? You need help from the computer. So what we are going to do here is, first, we are going to fix, so we cannot handle all the possible parameter values. So first, we will study the standard normal distribution. Standard normal distribution is the normal distribution with mu equals to 0 and the variance equals to 1. So we call this standard normal distribution. And then a standard normal distribution is usually denoted as z, because we are going to use this z often because almost everything will be approximated to z. So we use a special notation for standard normal distribution, and so z means z follows normal distribution 0, 1. So this is a fixed notation. And for algebra, to calculate the probability, even though we know the parameters, it is still impossible to calculate the probability by hand. So we are going to use computer. I am going to use Microsoft Excel or like other tools. When before the COVID, I used to distribute a table with normal distribution probabilities. It has a lot of numbers with probabilities, but actually that's outdated. These days, of course, no one uses paper to calculate probability. So you will need Excel. I recommend you to use Excel, or in case you don't have Excel on your computer, you may use Google spreadsheet, or you may search standard normal distribution calculator on Google or any search engine. And I am going to use Excel for demonstration, and in the next video you will need to use some calculator like Excel or normal distribution calculator web page, or you may use a scientific calculator, portable calculator, whatever. So you are going to need some help. Okay, let me stop here. I'm going to continue how to calculate the actual probability using normal distribution. Okay, see you in the next one. Bye.